Anyway, let's wrap up our discussion of multiple regression and correlation, because there are a couple of things that we didn't talk about that I want to talk about. We've got basically two types of purposes for multiple regression and correlation that I can see. What types of things do you imagine people use multiple regression and correlation for? What two types of questions? Two types of problems. We have multiple independent variables. This would be true of any multiple regression and correlation, right?
One cause how can affect the other. The relationship.
We want to understand the relationship between variables, right? But why do we not just stop with simple regression? So a simple regression is just basically correlating one variable with another and then determining the regression coefficients for that one correlation, right? So why do we do multiple?
We might have a partial correlation which actually give us each one of those effects alone and their interaction.
Yeah, so we have things like partial correlations and semi-partial correlations, which tells us something different than just a correlation, right? So a correlation can tell us something like, well, these two variables are related, right? And this can be interesting. We want to know if variables are related. But by doing a semi-partial or a partial correlation, what we can do is see if these variables are related when we've already controlled for some other variables. So this can help us to understand what's going on, how the variables are related. So the first purpose that I sort of see has to do with understanding. The second one has to do with prediction. So when we've talked about both the simple linear regression and also the multiple regression, we've talked about correlation coefficients and then also regression coefficients, right? And the regression coefficients are what? What regression coefficients are we talking about?
Slope.
Slope and intercept, right? Basically slopes and intercepts. And we're basing these, at least the ones that we talked about, on the partial correlation coefficients, right? And I said during one of the lectures, or maybe not in the lecture, maybe it was on the homework, but that if the partial correlation is statistically significant, what else is? Well, we determine significance by looking at the if the partial correlation is significant,
and
the semi-partial is also significant, and the regression coefficients, the slopes, are also significant, equally significant, right? So we have these correlation coefficients, which just tells us about the relationship between variables, and we can square them and talk about the percent of variances. But then we also have these other things, these regression coefficients, right, which gives us the slopes, and the constants, excuse me, the constants, which is the intercept. So let's look at the first one first. So with prediction, when we're making predictions, it's typically the regression coefficients that we're really interested in. Not necessarily the correlation coefficients or the semi-partial or the partial correlation coefficient. It's the regression coefficients. Why? That's a great question. Let's see if I said why here. No. Why? So, for multiple regression and correlation analyses, when people are trying to make predictions, they're typically more interested in the regression coefficients than the corresponding correlation coefficients, or the partial correlation coefficient. Why is this?
Maybe because the slope is makes the relationship between independent and dependent variables. So
we have this slope, which tells us the direction, well, the correlation will tell us the direction and the strength, but the slope that we compute from those tell us about, with an increase in this, how much of an increase we expect in this, right? In units that allow us to predict what the dependent variable should be. Right? So there was a question on the homework. Imagine that someone had a score like this on that and a score like this on this. What would you predict their test score was? Right? By knowing the slopes and knowing the scores for the independent variables, you're able to make a prediction about the dependent variable, right? And you use the slopes in order to do this. And this is really, really common in applied work. If you want to hire somebody or admit a student to a university, how could you use multiple regression or correlation analyses to select the student that would be most likely to succeed?
Making prediction.
Yeah, how do you make a prediction? Which students will succeed? The Turkish government does this.
In exam.
There's an exam, right? So you all take this big, big test. It's really, really important. And depending on your scores, this determines what university that you're going to get into, right? Along with everyone else's scores and everyone else's choices, right? So they're making this prediction about how well you should do in college. And we'll give the students that we're predicting should do the best in college the first choice, right? Let them go where they want. Is this a great way to predict whether a student will succeed? No, why?
Because we just consider the questions that we ask them. So we don't know the other variables.
What other variables? What other variables are there that could explain someone's performance in college other than their performance on this exam?
His performance in different exams. His sleep hours.
Yeah, so with one exam, you have like one shot at it. You're sick on that day, it stings to be you. You didn't get much sleep last night. Well, that one probably wasn't a very good idea. Right? So there's just one exam as opposed to multiple exams. What else? From what I hear, there are claims in the prep school that the exam performance really doesn't affect how students get through the English prep program. There's some students with really, really high scores that take 2 years to get out of English prep. And then you have other students who have never taken English before, and they're basically ready to leave before their year is up.
Maybe because they have ability to learn new language more.
So maybe there are different types of abilities, right? And the Tubatalk test doesn't measure your ability to learn English. What else is there?
How often they communicate with the language?
How often they communicate with the language? Okay, that may be true, but let's assume that all the students here have equal opportunities. I mean, everyone here has the opportunity to speak English every day, all day, right?
Some people want, some people don't.
Some people want, some people don't. But what other things? I mean, I want to know if someone, I don't care. I am not in the English prep program. I do care whether people get this or not. But ultimately, I want people to succeed in the university overall, right? And the English is just a small part of that. So what other things affect performance in the university overall? Not things like how much time you spend talking to your friends in English. So people have different skills. I was looking for something more like Siddharth said, motivation, right? Motivation. How motivated are people to learn and apply? What other things? If you guys wanted to go to America, to go to a college, what would you have to do for your application for them? They also require tests, most of them. Either the SAT or the ACT, have you guys heard of those? Standardized tests. So that part is the same. What else? GPA, your high school GPA is used to determine whether or not you can get into a university. Not just the test score, but GPA as well, right? Some people are really sort of bad during testing situations, but during the normal course of the year, let's say specialized testing situations, they're not great in. But in the normal course of things, they're able to do very, very well. So you have some students who might do very poorly on a standardized exam, but do really, really well in high school overall, right? What other things? Have they worked on other projects? What type of extracurricular things have they done? Have they just hung out with their friends, or are they involved with the charity? Are they involved with sports? Are they involved with other things? Hoping that that might indicate some level of motivation, perhaps, right? What other things? Letters of recommendation. Letters of recommendation are often important. right? And not just a letter of recommendation from someone else, but also things like a statement of purpose. Why do you want to come to this university? You know, why do you want to major in what you want to major? So they take all of these things to try to make some prediction, right? Not just looking at one thing. So you look at the qualifications of the applicants, however you want to determine what those qualifications are. To get some jobs, you have to take not just one test, but a bunch of tests. And not only do you have to take tests, but you have to interview with people. And as you're interviewing with people, they're making decisions about how well they think you're going to fit in at that organization. This is the same thing in graduate school. If you get an invitation to interview at a graduate school, a big part of the invitation is trying to figure out if you would fit in the program well. It's not whether or not they think you are smart enough or would succeed. It's, do they think you're a match for them? Right? So there are lots of things that can come into play. So if we know what qualifications predict success, then we can create a model, right, and use regression coefficients to create some prediction, and we can basically rate our people, find out, okay, they have, you know, these qualifications, she has those qualifications, he has this qualification. What are the predictions that we're going to make for these different people? What do we think their success level will be? And then we're able to make a decision, not based on a gut instinct, but on statistics. Salary. People, especially big firms, use multiple regression and correlation to try and figure out what salary that they should give people. So, given the qualifications of some person, how much should you pay them? What should pay be determined on? Should the amount of time that you've been working in the industry affect anything? Yeah, potentially. The more years that you have in a job, the more experienced you are. That experience can be really valuable for some industries, right? So you want to pay them more. What other things? I'm sorry. Creativity. They want to pay people for their creativity. I wasn't thinking about this, but they could. How can you pay people for their creativity?
For advertisements?
For advertisements. So you're working in a marketing firm, and you find that some people are producing more creative advertisements than the people that are purchasing, that are making the decisions about which advertisements to go for. Those people are producing more of those, so you want to pay them more, right? What else? Degree? Why are you guys here in college?
Our GPA, which we can show how we are successful.
With your GPA, you can show that you're successful, but a lot of firms aren't really interested in GPA as much as they are just have you completed a degree. Do you have a bachelor's? Do you have a master's? And then we'll pay people more depending on what degree they have, right? So if you want to make sure that your salaries are justly given, you should pay people based on their qualifications, not on whether they're Kurdish, or not on whether they're male or female, or other things like that, right? Whether people use multiple regression and correlation, right? So given these conditions, we have some conditions right now. We know how the humidity correlates with rain. We know how the direction of winds correlates with rain. We have an understanding about the relationship between these different variables that the meteorologists are interested in, right? And based on the conditions that we have right now, they're making predictions about what the weather will be like tonight and tomorrow and next week, right? So, lots of times there are many variables. We never got around to it in the homework, but I had lots and lots of variables for the test scores, right? We had test 1, test 2, homework average, number of submissions, number completed, and then I had scores for each of the homework assignments as well, right? So we had lots and lots and lots and lots of data. So the question is, if you want to make predictions, is which variables do you use to make the predictions, right?
According to what you are looking for.
So if we want to predict test 2 scores, I mean, we are looking for test 2 scores, right? Which of the variable should we use?
Test 1.
Test 1, okay. Why test 1?
Because it's before test.
Because it's before test 2, okay.
Actually, we can use all of them.
We can use all of them, she's right, we can use all of them. We could use all of them. What do you think would happen if we used all of them?
We will see how it affects
we should have different effect values for the variables. We should have different effect sizes for the variables, which we haven't talked about how to calculate, but they're based on the correlation coefficients. Right? They're actually based on the correlation coefficients of determination. So the squared values of those, telling us something about how much variance is being accounted for. Now, if we have all those variables in our regression model, we should be able to account for a lot of variance, right? But what about the semi and the partial correlation coefficients? Will any of those variables account for any unique variance? I don't know if it's that obvious. You say of course, but it might not be. In one of the, I think it was one of the homeworks, where we included all 4 predictors. So we had test 2 as a function of test 1, and as a function of homework average, and as a homework of number completed, and the number of submissions. And most of those didn't have any significant contribution by themselves, right? Any unique contribution, once you accounted for all of the rest. So when we did the correlations one by one, we found that each of them was a significant predictor, right? But when we threw them all in, there was only like one, I think, left that was a significant predictor, right? If we threw in all of those other, I would guess that probably none of them would be significant predictors because you would be left with very little variance, right? Even just due to chance. So the variables that we should use should be variables that explain unique variance in our dependent variable. We don't want to throw everything because not everything is predicting a significant amount of variance. If the partial correlation coefficient is not statistically different from 0, that means that there's no unique relationship. And if there's no unique relationship, should you be using it to predict? No, right? So let's only use the variables that we have a unique relationship for. So we use a statistically significant variable. So how could we do this? I'm going to go reset the camera. Okay, so how could you do that? What?
We did it with core test to calculate.
We did core test. The core test just calculated the simple linear correlation, right? And whether that was significant or not. Okay, so let's start with the core test. What do?
We take our dependent variable.
We take our dependent variable.
And
What is what?
The sign.
tilde.
Theta?
Tilde means
Tilde. The dependent variable is a function of
independent variables.
So but this is linear model.
Yeah, it's
all of them or just one of them? Because core test is just for one.
No, that's cortex. It's the linear model.
Linear model, LM. Dependent variable is a function of all of our independent
Not
variables.
all of them, we just specify one of them with the plus sign should be.
Okay, so we specify 1 or 2 of them. How do you pick which 1 or 2 of them that you're going to specify? Alright, so I'll give you one potential way, and this, as it turns out, like a lot of my examples, is not the right way you should do this. So maybe you could do an MRC with all of the variables, right? So the dependent variable is a function of all of the independent variables, right? And you want the ones that have a unique, that explain unique variance in the dependent variable. So just look at the results of that output and see which ones explain for unique variance, and then base your model on that. Throw everything else out, right? Maybe. So the problem is that some variables that don't explain unique variance with others could by themselves. This is the problem that we came to when we had all of the 4 independent variables trying to predict test 2. So each of those predicted unique variance, but not all of them did when we included all of them in our model, right? So one solution to get around this is known as stepwise regression. Stepwise in the sense that you're going to go through a bunch of steps. Basically what you're going to do is a multiple regression analysis multiple times. So let's start with the simple regression for each variable to find out which variable explains the most variance, right? So we'll try to predict test 2 scores from test 1 scores. We'll see how significantly that predicts. Then we'll do the same thing for our homework average. Then we'll do the same thing for all of the variables that we could potentially be interested in, right? And we'll see which one explains the most variance, right? So we will then include this. This one's explaining the most variance. It's the most statistically significant, so let's include this in our prediction model. Does that make sense? So if it's a significant predictor, we're going to include that variable in our model. If it's not, we're just going to stop and say nothing that we have is predicting the outcome, right? If you design things wisely, you should have something that does. Okay, so we're going to include that variable if it's a significant predictor. Then what? So we predicted test 2 from test 1, test 2 from homework average, test 2 from number of submissions, test 2 from homework 1 scores, test 2 from homework 2 scores. We did all of those and we found that test 1 scores was the biggest predictor, let's say. Okay, so now we've got test 1 in there predicting test 2. Now what? It's possible that other variables also contribute, could increase our ability to predict, right? Significantly.
Can we do multiple, like linear models, but for multiple?
So maybe now we'll do multiple linear models, right? So we have test 2 is predicted by test 1 and homework average. And then we can do a different linear model. Test 2 is predicted by test 1 and number of submissions. And a different linear model. Test 2 is predicted by test 1 and homework 1 scores. For all of the variables that we have left, right? And then what we can do is look and see which of those variables has the highest partial correlation coefficient. The highest in the sense of statistical significance, right? Which one has the smallest p-value? So we start with the simple regression for each variable. We base our initial model on the value or on the variable that explains the most variance. Then we do a whole bunch of the multiple regressions for each remaining variable and find out which of the remaining variable explains the most of the unexplained variance. Okay, and then what do we do? We combine them, okay? That's actually what we did when we did this, right? We combined the best model that we got from our simple regression analysis with all of the potential other variables.
But now we can add submissions and homework completion.
Yeah, so maybe submissions was the biggest predictor after we accounted for test 1. So now our model is test 2 is a function of test 1 and submissions, and now we, in addition to this, we add on homework average. We do another one where we don't include homework average, but we include homework 1 scores. Or all of the other possibilities. So basically, we just keep doing this. We go through this again and again and again until we don't have any variables accounting for any significant amount of unique variance. Then we stop. Because after that, nothing's accounting for anything. Everything else has been accounted for. So we stop. Does that make sense? This will give us something that predicts at least the data that we have really well. You can also start with all of the variables. So we started with no variables and we added them in one by one. You can also start with all of the variables and take them out one by one based on not which is the most statistically significant, but which is the least, right? What has the smallest t-score? What has the smallest p-value? And pull them out one by one until we're left with the model where all of the variables that remain are accounting for a significant amount of the variance. Okay, some problems with stepwise. One, it's atheoretical. Atheoretical, what does that mean?
Not
It means that it's not theoretical. What does that mean? It could be practical. So this is a more common situation in applied work, right? Where maybe it's not the theory that's the most important, but your ability to predict correctly, right? So sometimes we can predict things very well without maybe a good theory of why it works. We happen to find that this variable predicts that. We don't know why. We have no theory that explains it, but it does, right? So the variables aren't included for their theoretical importance, but for the amount of variance that they explain. This means that some good variables, some variables that theoretically should be included, that theoretically should explain a lot of the variance, might never make it in the model because other variables that maybe aren't founded so much in theory explain more. So,
What should we do?
what should you do? Well, if you are trying to make predictions, it's not necessarily, if you're trying to make predictions, you don't necessarily have to have a theory that explains why the things work. I mean, it's an important scientific thing, right? Science is interested not just in making predictions, but in also explaining why we're making the predictions, right? That's where the theory comes in. That's where the understanding comes in. But from the predictions just by itself, maybe not such a big deal. It's also prone to overfitting. The model can fit the sample data, but it might not fit the population loss. Think sort of like restriction of range, right? You had a restriction of range, and you based your model on that. And the model based on that didn't necessarily capture all the complexities in the population. And because your sample is finite, and you don't have all of the population available, some things that are just statistically significant due to alpha error, things that really don't explain, it's just an accident, the stepwise regression can, what am I trying to say? The stepwise regression can include that even though it shouldn't be included, right? If you had more data, you wouldn't include it. So you could be making predictions based on flukes. So what do you do in that situation? Well, as you're making predictions and you're gathering more data, you can compare your predictions to the data and then try to revise the model as you go along to get better predictions as you go. All right, so that's basically prediction and MRC. There's also the understanding, which is more heavily dependent on the correlation coefficients or the semi or partial correlation coefficients. It's much more common in theoretical work, scientific work, and the work that people at universities are doing. So, hiring and admissions. What variables should uniquely predict academic success? Right? I'm not asking now, what variables can I make the best prediction for, different students with? But I'm trying to think, what things should explain collegiate success?
Yes.
Well, motivation should explain collegiate success. How can I measure motivation? By coming up with some measure of motivation and seeing if that predicts collegiate success once you've already included the things that are already being used to predict success, like the two test scores, right? So test scores are supposed to predict success. Let's control for that. Once we've controlled for that, is there anything left explained by my motivation scale? Is this type of motivation different than that type of motivation? So if any of you guys are taking Sammy's social cognition course, has he talked about like intrinsic and extrinsic motivation?
Social cognition is in practice.
Oh, that's Ibrahim. Has Ibrahim talked about the intrinsic?
No.
Any of you guys had Sammy talk about intrinsic, extrinsic motivation? Did any of you guys know it? Yeah.
In creativity.
In creativity, you talked about it. Like, what's the difference between intrinsic and extrinsic motivation?
Intrinsic is like, unless we talk about intrinsic, but we don't talk about.
I'll give you 100 liras if you can answer this correctly. I actually won't. I'm not going to give you 100 liras. There was an example. Sorry, no 100 liras. That's above my budget. Extrinsic motivation. How much motivation do you get when you have some external reward, right? Are you going to perform better if I give you this cash, right? This is some external reward. Extrinsic, it's coming from outside, not coming from within. Versus the intrinsic motivation, like think about Maslow's hierarchy of needs. That the top one.
Achievement.
Yeah, it seems like there was a different. It was related to actualization, self-actualization, right? Which is related to achievement. Right? How much do you want to get the answer right? Because you have pride in the work that you do. You don't care if people are going to pay you for it or not. You want to get it right because you care. Right? Is there really a difference between these two things? Maybe not. Maybe Sammy's full of crap. Not full of crap. But how could you test that? Well, you could find a measure of intrinsic motivation and account for some outcome variable, like performance on some task, as a function of extrinsic motivation, and then see if, by including intrinsic motivation, if that accounts for anything else. If these are really different things, they should account for something else, right? If they're the same thing, they shouldn't account for anything else. So we can use it to understand things. With salary, after accounting for qualifications, are there any gender-based salary differences? Is there discrimination at the place that you're working? Are they paying women less than men? Now, earlier, when people were making these claims, oh, you know, women, they're getting paid less than men. Corporations would say, look, we're not acting biased. Right? We're not doing anything wrong. We're paying them what they're worth. And what things did they say about the women? Why are the women getting paid less than the men?
Because maybe they have low qualifications.
Maybe they have lower qualifications.
But there are some cringes about that. Maybe they can be wrong. Because of that, they can work less. But when a child is sick, you have
So if they're a mother and they're going home to take care of their child and they're working at the marketing firm, instead of trying to come up with some new advertisement idea, they're busy cleaning up poop, right? So they're not able to be as creative. Well, I would pay you more money, but you're just not as creative as that guy. You're not producing as much, right? So the companies, they would want to say these things. They want to say, look, we're not biased. We're not paying women less because they're women. We're paying them less because they're not performing as well. We're paying them less because they're doing different jobs. The men are doing one type of job, the women, they're secretaries. The secretaries aren't as valuable, right? But now as there is more gender equity, at least in the jobs that men and women are performing, now you can do interesting things. Like, let's predict salary as a function of time in the job, educational level, type of job. Is it administrative, managerial, executive, all that stuff. And now, after accounting for all of these things that should make a difference in salary, now let's include sex. And if we're not biased in the way that we're paying our employees, sex should not uniquely account for any more variance. If it does, the company has a problem. And in making compensation for the people that have been affected, they'll probably also use multiple regression and correlation analysis to make predictions about what the women should have received.
based on their qualifications alone. So you can use multiple regression correlation analysis not just for prediction or understanding, but for both, understand and make predictions. So it's not like you have to do one or the other. Okay, so let's wrap it up. Multiple regression correlation is extremely useful. It's extremely flexible. In graduate school, I took a course. We spent one entire semester on correlation and multiple correlation and semi-partial correlation coefficients and looking at them this way and looking at them that way and how do you include categorical variables in your correlations. So there are tons and tons of things that you can do with the techniques that you learn. How you use multiple regression correlation depends on the work that you're going to do. And it depends on the questions that you're trying to answer. So the last few classes are really just a tiny little piece of the world of regression and correlation that's out there. Okay. All right, so let's talk about the data that we've worked with so far. So far we've talked about binomial. We've also talked about everything else. What type of data were we dealing with in the binomial? The data that we were analyzing. So the variables were random. We talked about random sampling using the binomial, and we said that a flip of a coin is approximately random, right? So is there a difference between that and everything else? No, except for like the paired and the repeated measures things. Basically, we're doing completely random samples where one observation is independent from the other. Like when we did paired t-tests, not every observation was independent, right? We had a special exception. Same thing with repeated measures. But otherwise, all of our observations were found using random sampling and independent observations. What else? There were lots of questions throughout the semester that people would say, P suck! And I would say, no, that was the binomial. You guys remember that? What's the answer to this? What should we include? P suck! No. It's binomial. What was P suck? It was the probability of successes. And what we were looking at was the number of successes that we observed given some theoretical probability, right? So with the binomial, what we were looking at basically were frequencies and percentages. We're predicting 50 flips out of 100 should come up heads. What's the probability of observing something as or more extreme than 38 heads, given that prediction, right? So we're working with frequencies, just a number of observations. Everything else has been something different than frequencies. What has everything else been? We've been working with values. That's absolutely right. What type of values? We have used descriptive statistics to communicate information about those values. But what are the values? Some of the values were wrapped up in descriptive statistics. What were we doing when we did a t-test? Take a sample.
Subtract the population.
You're on the right track.
The formula was you subtract population mean from sample mean.
So we had something.
Yes. Divided.
Right?
The standard deviation.
Oh, divided by the standard deviation. So let's just say, in fact, let's not even do that. Let's just say standard error. Right? And the t-test, this would be, so you're right, I was thinking you were talking about something else. But you said the sample mean minus
the population mean, the hypothesized mean, right? So what are we interested in? We're interested in,
The difference.
we're always interested in p-values. We're interested in the difference between,
Some population mean and what we find is some.
can you say it in one word? We are interested in the difference between
Mean.
means. We're interested in the difference between means, right? That's what we did with 1 sample and 2 sample t-tests, right? Is there a difference between these means? From the hypothesized difference? Is there a difference from this mean from the hypothesized population mean? If we pair people, right? Is there a difference between means? This is the same thing we're interested in when we're doing analysis of variance, right? We're talking about means, right? Are these means different from one another? And then we got to regression, which is more than just means. There's something like a mean, right? We're making a line, and we're basing that line on the means. And we're also basing that line on not just the means, but on the slope. And the slope was computed by correlation, which was computed by covariance, which is like a what? It's a special type of variance, right? Basically, everything else, when we're looking at means and variances, there's some type of variance, a covariance, or a standard deviation, or the standard error of the means, or the standard error of the difference between means, but basically all those boil down to some type of mean or variance, right? So today we're going to go back. We're going to go back, not to the binomial. We'll do the binomial quickly, but we're going to go back to frequency data. So the test that we're going to do today is the chi-square, which is represented by the Greek letter chi, which looks like an x, but it's different. So if you see x squared, think chi-squared, not x squared. Yes?
We had something similar when it was f value.
Yeah, back when we were doing the ANOVA, we had f.
So because
X squared.
Representing the division or something.
We talked about
Squares.
sum of
It
squares.
was homework.
Yeah, so there it is. We discussed the sums of squares, right? The variance is just a weighted sum of squares. We're summing up the squares and then we're dividing by n, or n minus 1, depending on what type of variance that we will want to get. But yeah, basically, the sums of squares we talked about is distributed according to the chi-square distribution. And this is the graph that I showed from the previous class, right? Where you had the different chi-square distributions depending on the degrees of freedom that you had. So Pearson, this segues so well from correlation to here because we were talking about the Pearson correlation. Pearson was also the one that figured out that frequency data, not by themselves, but appropriately massaged, appropriately weighted, basically are described pretty well by the chi-square distribution. So let's think about the questions that we can ask in relationship to frequencies. So we can say things like, do the frequencies of observations in some categories match some theoretical distribution? This is exactly what we were doing with the binomial. We're predicting. We have this hypothetical distribution, this fair coin. And in the fair coin, half of our observations should be heads, and half of them should be tails. Right? This is a hypothetical distribution. And then we flip coins and we gain our observations. And we use the binomial test to figure out whether or not the observations that we had were sufficiently different from what we would expect to have. Right? So we're going to be doing something very, very similar here. You could ask things like, are there equal numbers of conservatives and liberals in Turkey? You could ask things like, do 10 10% of people identify as something other than heterosexual. So some of you may have heard, like, there are different estimates about the prevalence of homosexuality in different cultures, but one of the commonly referred to percentages is 10%. People say that, look, even in cultures where it's not expressed, where people aren't open about it, 10% of the population is gay. Just aren't out. Is it correct or not? So you have this idea, this hypothetical distribution. 10% of the population in Turkey should be gay, right? So you can take a sample. Let's take 100 random people. From that 100 random people, how many should be gay? 10. That's a frequency, right? How many should not be gay? 90. That's another frequency, right? So we have predicted frequencies, and then we'll have the observations, whatever they turn out to be. Does personality type depend on sex? Are women more likely to be extroverted, narcissistic? We can talk about some frequency distribution. We can look at the frequency of the different personality types in the overall population, and then look to see if women share that same frequency. Right? Is some variable normally distributed? We talked earlier about, okay, in order to run these tests, we need to, assume that the variable is normally distributed. And we didn't talk about how you can test that. But you can test it with the chi-square. Because you know that a normal distribution, if you standardize the distribution, so many percent of the value should be within half a standard deviation of the mean. And so many should be above half, or be between half and 1 standard deviation above, and so many should be between 1 and 1.5 standard deviations above. You can make predictions about what the frequencies of observation should be for each of those groups. Right? And then look and test to see if the data that you actually observed, if it fits into those categories in a way that's predicted by the models. Alright, let me ask you. We have 52% of the Shahir students are male. I'm just making this up because I don't know exactly the numbers. Let's say 52% of the students are male. How many are female?
48.
48. How did you know that? Oh my goodness.
Because all of them was 100.
All of them is going to be 100%, right? So when you know the one thing, you know the other. How many degrees of freedom are there? One, right? You know what percent are male? You know what percent are female. 1 degree of freedom. All right, is the distribution of sex in psychology the same? Is the psychology major, the students in the psychology major, are they like Shahir students? Or is this like a separate population? Right? Let's take a random sample. Take 50 students. And we'll figure out whether they're male or female. And none of them say that they're males, and 41 say that they're females. Is this statistically significant?
Yes.
It is. But how could you know if you didn't know? Use chi-square. Beautiful. Or what else could you use?
Binomial.
You can use a binomial. Yeah, sure. We can use binomial for this. Absolutely. So you just do p-binom. The probability of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Of 9 or fewer students, plus 1 minus the probability of getting 42 or fewer students, right? Remember, we had to do some funny adding and whatever. You can go back to those lectures if you want. Anyway, here's the probability. So it's pretty small.
You reject.
We would reject the null hypothesis. That's absolutely right. Binomial, actually, this is a better test. I really sort of feel bad about teaching you the chi-square. I love binomial. It's beautiful. It's accurate, it's precise, calculates exact probabilities. The chi-square, we're just estimating them. So remember the earlier slide. Here, we said these distributions sort of fit frequency data well. Not perfectly well, right? And a lot of the statistics that we're doing with, we say, okay, that's good enough. It's not normal, but we have a sample size of 30, good enough, close enough, right? Binomial, you don't need to do that. You can calculate things exactly. With the chi-square, we are just approximating. Okay, so why am I teaching you the chi-square? Well, because it's incredibly popular. Chi-square is all over there in the literature. You will find people using the chi-square all over the place. Binomial's better. Chi-square is pretty darn good. So it's important for you to understand what the chi-square is, so you understand what it is when you see it, and you will. That said, don't use it for your own research. Use the binomial or
Why?
the multinomial. Because with the binomial, we can predict exact probabilities. We can figure out exactly the probability, not a guess that should be pretty close.
So if it's chi-square, we have errors, more errors?
We will see. We will see. Yes, we will see. Okay. So the formula for chi-square. Here it is. It's not actually that long. It's just I have the words in here, so it looks big. So chi-square is equal to the sum of something squared divided by something else.
It's same.
What? So what are those somethings? The observed frequency. So we had 9 males that we observed, and we have some expected frequency, right? The hypothesized frequency. 52%. We'll see what it is in just a minute. Anyway, so we're squaring the difference between the observed frequency and the expected frequency. We're squaring that, and then we're dividing it by the expected frequency. So no, this is a sum of squares. Chi-square distribution is a distribution of sums of squares. So what types of squares are we summing?
Variance?
It's something very close to variance. Something very close to variance. With variance, we had something like each value minus the mean, right? In the mean, when we talked about the mean, I said that the mean is our best guess about what the value should be, right? It's our best guess. It's our best estimate. It's what we would expect, right? So what we did with variance is we took deviations. It was a deviation between what we observed versus what we would expect, right? Here, it's exactly the same thing. It's a deviation between what we observed and what we expected. But it's a deviation in frequencies. We expected 10 and we saw 12. 12 minus 10 is 2. Square it. 4. Divided by, I forget what I said we expected, whatever the expected one was. Right? So there are deviations between what we observed and our best guess as to what we would observe. This is very similar to our formula for variance. It's not identical. So let's look at how it's not identical. So there's the formula, much more condensed. O means observed, E is perfect. So chi-squared is the sum of the squares of the differences between observed and expected divided by what we're expecting. So the sums here that we are squaring are weighted, right? That is this part right here. We're weighting it, right? If E is big, then this sum of squares will be smaller. If this is really small, this sum of squares will be bigger, right? So we are weighting the sums of squares. For variance, all of the squares are equally weighted, right? We're saying that the weight is equal to 1 over n minus 1 for the unbiased estimate of the population variance. Right? For the chi-square, the weights can be different for each squared variation. Because we have an expectation about how many females we should observe. And we also have an expectation about how many males we should observe, right? So it's possible that we are going to have different expectations for our different groups. Why? Why is this? Well, imagine that you expected 10 observations, that you saw 20. And also imagine a different situation
where you expected 100 observations and you saw 110. What is the sum of the deviation squared here?
100.
For which one? For both of them. The sum here is the same. But do one of these two examples seem more unusual? The first one, this seems more unusual than this one. And this is the same. Why would you say it seems more unusual?
Because when you compare it to 10 is 200%.
Yeah, 20 compared to 10, you've got 200%, right? You have 2 times more than what you would expect. Whereas if you look at 110 versus 100, you only have 10% more than what you expect, right? So compared to what we were expecting, the first seems a lot more extreme. So dividing the squares by our expectations allows us to give more weight to more extreme deviations. What does what mean? So in the sense that we were talking about here, 10 more than 10, we basically have twice what we were expecting. It's like if I opened up my pocket and I thought that I had like 10 liras, and I'm like, whoa, okay. I do have more than I expected. I did not expect the 50 to be in here. I thought I had like 2 or 3 20s. So I have a lot more than what I expected, right? But if I thought like, oh yeah, I've got like $5,000 in my wallet, and I pulled out, I'm like, okay, 200, 400. I love the 200 or the 200 lira bills. They're so cool. Okay, 800, whatever, 100, lots of hundreds, and 50 more. 50 more. Then what did I say? 8,000, 5,000. 50 more. It's like, right? Which is why when I offer a prize for getting like the right answer, don't offer 50, because that's a lot compared to what I normally carry. But 5, maybe not so bad. Okay, does that make sense? So this is like a whole lot more than what we had expected. And even though this absolutely is the same amount more, if we compare it in a percentage sense, or ratio, which chi-square is, it's much larger. Yeah.
We have to actually sum close to the variance, because in the variance we divided by n.
Right, and we divided, at least for the bias one, we divided everything by n. So there is a difference between this formula and variance. He's exactly right. With the variance, all of the weights we had for each thing was exactly the same. It's not the case here. The weights are different. To account for the fact that some deviations, even though in the absolute sense they may be the same magnitude, in the sense of a ratio, that's really sort of unusual. Okay. So back to our example. So here are the observed frequencies that we have. Here are the expected percentages. Notice this is expected percentages, not expected frequencies. In the formula that we had observed frequencies minus expected frequencies, not expected percentages. So we need to get from the percentages to frequencies. How do we do this?
Divide by 2.
Divide by 2? How do you get that?
Because we have 50 total.
So we had 50 total. If you imagine that 100 compared to 50 is twice, if we divide all these by 2, we should get what we're expecting. That's basically right. In fact, that is right. I was not thinking about it like that, but the math, the algebraic manipulations are going to give us the same type of things. I would have just multiplied these numbers by the total there. They'll give us the same thing, right? Okay. I was going to say I prefer doing it multiplying these times that, because not all the time will you have a nice something that's nicely divisible into a factor of 2. What if I had 183, observed, right? So if you do it this way, It should be easier for you. Okay, so we're going to multiply the expected percentages by the total number of observations. So 0.52 times 50, that should give us 26. Man, you guys are smoking. So expected frequencies for the male, 26. It's 0.52 times 50. And female, that's exactly right. If we have multiple categories, we can still use chi-square. Because chi-square isn't limited to 2. We would have more degrees of freedom. That's exactly right. So, favorite sports teams, you could talk about Galatasaray, Fenerbahce, Beşiktaş, or other. You could include as many as you wanted to. You could talk about religious identification, Christian, Muslim, Jew, Hindu, whatever, atheist, other. Personality type, introverted, extroverted, narcissistic, whatever. Talk with Sammy. All right. Let's imagine a theoretical football example. So we ask students at Shahir what football team that they like. So we have 124 people say they like Galatasaray, 97 like Fenerbahce, 283 like Beşiktaş, and other 28. Sorry, Trabzonspor and Belediyespor. Belediyespor. Yeah. All right. How many degrees of freedom do we have?
3.
3. Right. K is 4. K minus 1. 3. Beautiful. So in R, I created something very simply. Observations: 124, 97. 283, 28, right? I've used C to basically put all of these things together. Just makes a list of all of the observations that we have. Okay, now our total sum of the obs, that will give us the total number of observations that we have. Now the expected percentage based on the Istanbul population, imagine that these are the percentages. All you need to do is multiply the percentages by the total to get the expected values. So you could do something like this. So expected equals, okay, 34% of the total, 29% of the total, 27% of the total, and 10% of the total, right? And if you do this x, you'll get these values right here. Now chi-square, what is it? It's a sum, okay, we have the sum of what? Well, we have the observed values minus the expected values, or frequencies, squared, all of that divided by the expected values, frequencies, right? And the sum of it. Boom, there it is. Wow, it's a big one. I was a little biased when I created this example. So 1 minus chi-squared chi2 df. So this is using the cumulative probability mass function. So 1 minus that to give us the bit on the tail that's more extreme. 0. What does that mean?
Reject.
We are going to reject a null hypothesis. It shouldn't actually be 0. It'd be like 0.999999 something, but it's goes so far that it's beyond R's ability to compute to that many digits, and it just gives you 0. Reject it. All right. Let's say we have 2 categorical variables. We can have any number of different ones. Sex is categorical, male, female. Gender, I'm not sure why I included that. There are differences between sex and gender. Political affiliation, so on. Personality type, whatever. Let's work with major and personality. We'll talk about psychology, engineering, and other. And we'll talk about just introvert and extrovert. Okay, so the observations are easy. These are just the things that you observe. So here is one possible way of seeing all the things that we observed, right? So we had 28 psychology majors that were introverted. We had 47 that were extroverted. We had 39 engineering majors that were introverted, and 24 that were extroverted. And we had our other majors that also we had introverted and extroverted. Why do you think I have the totals there? Why did I put the totals up there? Do we need the totals?
If we have to calculate percentage.
if we have to calculate percentages, totals are going to be helpful, right? That's exactly right. How do we get our expected values? We use percentages. We earlier multiplied the percentages by the total. So we're going to do the same thing here. We find the percent of students that are in each major. So in each major, 75 divided by 315, well, that's the percent that are psychology majors. 63 divided by 315, that's the percent that are engineering majors. In our sample, right? 177 divided by 315, that's the percent that are other. And we can do the same thing for introverted and extroverted. 152 divided by 315 gives us the percent that we're introverted. 163 divided by 315 gives us the percent that we're extroverted. All right, so we find the percent of students that are in each major, we find the number of students, or the percent of students that have each personality. We can multiply these percentages by the total. Percent of students in the major times the percent of students with that personality times the total. So our expected introverted psychology students is 152, number of introverted divided by the total, that's the percent here of introverted students, times the percent of psychology students, times our total number of students. Yeah? Why did we multiply? Why did we multiply the three of them? Let's go on to the next thing. Maybe this would be more obvious. You could multiply the number of psychology students by the percent of extroverted. So imagine you have whatever percentage extroverted and whatever percentage introverted, right? If these two variables are independent, if we had, let's say that this was 45, I don't know what it is, but let's say this was 45% of our students were introverted. If personality and major were independent of one another, not only should 45% of the students be introverted, but 45% of the psychology majors, right? I see a lot of shaking heads, and we are out of time, so we will come back to this.
The value of introverted psychology and extrovert is the same. Which one we calculate?
This or this, are you saying?
Yes.
These are algebraically equivalent. We'll come back to this slide next class and finish up chi-squared. Last class we finished on this slide, and there are a couple of things that people asked, and I wanted to cover those things now. The first one was about whether or not these two things were equal, whether the equations were equivalent. So I said we multiply the percentage of students that are in each major. So we had this. So this gave us the percent of students that were in the psychology major. Right, so the 75 comes from here, 315 comes from there, times the percent of students that are introverted. So this comes from here, that again comes from here. And then multiply those two percentages together, and then multiply that whole thing by the total number of students that you have. If we look at this formula, we don't have all the pieces. So here we just have 152. So that's this times this. Well, that's the same thing here. But this 315 is not there. What happened to it? So notice that this 315 here, there's a 315 there and a 315 there. We're multiplying all these things together. So we can cancel one of the 315s if we want. So I cancel this with that to give us this times that. You could cancel it the other way if you wanted to as well. Now, there was a question related to this. Like, how on earth, why on earth would we multiply the percentages together? Think about the percentages. Well, represented in the form where you divide it by 100. It's like a probability, right? When we talk about probabilities, 0.05 probability means that 5% of the time we should reject the null incorrectly, if we're talking about alpha, right? So we can talk about it as a percentage or as a probability. Now, the chi-square that we're dealing with here This is a chi-square test of independence. Chi-square test of independence. Now think back very early on to the beginning of the semester when we talked about variables, and we talked about independence, and we talked about probabilities. And we said that if two probabilities were independent, then we could multiply them together to find the, I'm going to get it wrong, the intersection, right? So the probability of A and B, the intersection of those two things. If A and B were independent, it was just the probability of A times the probability of B. You guys remember that? So if we go back to thinking about 2 points, what's the probability that I will get ahead and ahead? Right? So the probability of getting ahead on the first is 0.5. The probability of getting ahead on the second, if the coin is also fair, is 0.5. The probability of getting ahead and ahead, or ahead intersecting with ahead, is 0.5 times 0.5, right? And we could do the counting rules and see if we can get a head, head, tail, tail, head, tail, tail. We have 4 possibilities. One of those was the intersection, right? And to find the probability of that intersection, we just multiply the probabilities together. So, what we were doing here, basically, if you think about these probabilities, right? If you want the probability to find this, all you need to do is multiply the probability of psychology by the problem of introverted, right? If they're independent. We're going to test to see if they're independent. That's what the chi-square test is about. The null hypothesis is that they are independent, right? The variables are independent. So since we're assuming it's independence, that's why we can multiply this one by that one, and then multiply by the total, right? Because if we didn't multiply by the total, we would just have a probability here. But we don't want the expected probability, we want the expected frequency. We know the total frequency, so if we have the expected probability, we can multiply that expected probability by the total frequency, which will give us the expected frequency for that. If they really are independent. Did you have a question?
Independent, you mean the chess thing? We had like 16, number of pawns is the same.
Yes, yeah, when we talked about the chess. What's the probability of getting a black king? Well, we have the probability of black. We have the probability of a king. If we multiply the probability of black times the probability of king, we get the probability of a black king.
And this is independent.
Right, that's independent.
So you're assuming the same thing with psychology and introversion?
Yes, yes, that's what the chi-square test of independence is about. We're saying, you know, is there a difference in introversion between psychology, engineering, and other majors? Is there, you know, a difference? If there's no difference between introversion and those things, then introversion and major should be independent of one another. So we are setting up our expected values to look for independence. Right? If we had a particular expectation about, well, we think it's going to be twice as high for here as for engineering, we could set up a different expected. But since we want to test and see if it's independent, we're going to multiply the probabilities for the different majors by the probabilities for the different personalities to see if there's an independence. We could do this with other types of things as well. Gender and religious affiliation.
Can you give us like 2 examples of independent results and non-independent results like explained by the test?
I'm sorry, I don't understand your question.
We made the test. How can we figure out whether those are actually independent according to what we assume or not?
Well, so the chi-square, what it's going to tell us, so we calculated the chi-square for other hypotheses before, right? We got an observed chi-square value, and then we compared that against the cumulative probability for the chi-square distribution with the appropriate degrees of freedom, right? To see whether or not that was different from what we would expect
just do the statistical variation. So we're going to do the same thing here. So what we're doing is we're going to compute a chi-square value. And then if that is a lot bigger than it should be, based on the degrees of freedom that we have, then we'll reject the null hypothesis and say that there is sufficient evidence to conclude that these variables, major and personality, are not independent. Okay? If we would fail to reject, we would say that there is insufficient evidence to conclude that these two things are not independent. Right? Okay? All right, groovy. So here are the expected values. So if you want to go through this by yourself, just figure out these percentages or these probabilities, multiply them by those, and then multiply that by the total, and you should come up with these numbers. So we have our expected, we have our observed. Now what can we do? Chi-squared. And how do you do that? Observed minus expected squared divided by expected, and then sum all those things. So I've done this using R. Speaking of R, so we don't have a lot of classes left, and some of the things that I would teach you in R, they're fairly simple. So like on Friday, I'm not going to have like a lab day. We're going to have a normal sort of class day, but as I cover the different tests, I will show you how to do them in R as we go. Okay? If you want to bring in computers and follow along, sure. Okay, so what did I do? So I said intro. So the scores for our different majors, each one of these scores represents a different major. So our scores for the introverted group were 28, 39, and 85. 28, 39, and 85. For extroverted, we have 47, 24, 92. Extroverted, 47, 24, 92. Right? So I'm just creating those two variables that have the introversion scores for the different majors and the extroversion scores for the different majors. Now I got the total for the intro. I just summed up all of this, and that will give you this. I also did total for extroverted. I summed up those, it gave me this. If I want to get the totals for the different majors, all I have to do is add intro and extra, and I will get 3 values, which will tell me these totals right here. I also got the total, or the overall total, which is just the sum of the total for introverted and extroverted as well. Okay, what else do I have? To compute the expected, I multiplied the total number of majors by the total number of, the total number of, where is it? Total majors. Right, total majors by the total for intro divided by the total. So the total for intro divided by the total, that's the percent, right? The percent that we have that are introverted. And now this T majors, I'm multiplying each one of these by this percentage to come up with the expected. So if we go back, that's like I'm doing this. I did, except here, I didn't multiply the number of psychology students, I multiplied the number total. But we remember we can cancel out whichever one that we want. So basically, for each one of these, I multiplied by the probability of getting introverted or extroverted. So I did it for intro, I did it for extra, and then calculating the chi-square from here on out is the same. So I have my observations. I put the observations together, so I have all of my observations, the intro first and the extra. Then I have my expected, right? Which is just the expected for intro and the expected for extrovert. Then chi-square is just the sum of observed observations minus expectations squared divided by the expectations. So boom. We can have R calculate the chi-square for us like this. And it turns out to be 8.3 approximately. Now the question here is, what are our degrees of freedom? 1. 2. 3.
No, 2 multiplied 3.
2 multiplied by 3. 5. Well, 2 multiplied by 3 would be 6, but you're saying 5.
5 because
So we have 5 groups, right? 5 groups. Or, I'm sorry, we have 6 groups. So if we know 5 of those groups, then we know the 6th one, right? Now that seems like it could make sense, but that is not the right answer.
maybe we
You
have
again.
3 level.
We have 3 levels of the first factor, right? Or 3 levels of one variable. Okay, so how many degrees of freedom do we have for that?
2.
2.
And for the second one, we
For the second variable, we have 2 levels. 1 degree of freedom.
Multiplied.
So if we multiply the degrees of freedom for the one variable times the degrees of freedom for the second variable, we'll have 2. Why did you think of doing it like that?
Because in ANOVA we did for in a
That's what we did for ANOVA. That's what we did for ANOVA. So it's just like the degrees of freedom for the interaction in ANOVA. We find the degrees of freedom for the one variable, the degrees of freedom for the other variable. We multiply those 2 degrees of freedom together. Right? And it makes sense. Imagine, once we know this one, we know that one. Once we know this one and this one, we know this one. But now, since we know both of those, we also know this one. And now that we know this one, we know that one too. Right? So we only have 2 degrees of freedom for this particular design. All right. So now all we need to do is do 1 minus p chi-square, which is the p chi-square is the cumulative probability, which will give us, if we were to draw the distribution, I think it's something like that. So the cumulative probability will give us all of this, but we don't want all of that. We want what's left over. Right? So we use 1 minus p squared to get that, and we find 0.015. Reject it. That's exactly right. Okay, so some assumptions in the chi-square. Just like in our other test, we had some assumptions. Simple random sampling, a sufficiently large sample size. This is important because the chi-square, right, it's the chi-square distribution describes sums of squares. And it describes a particular type of sums of squares. It describes sums of squares for variables that are distributed normally. But here, we don't have a variable that's distributed normally. We have a variable that's distributed something like a binomial. But we have, it's not just one, there are 2 states that it can be. It's not just a success or a failure. It's psychology, engineering, other, right? Which of those is the success? Which is the failure? So this is a multinomial. But similar to the binomial, as you increase the sample size, you get something that approaches the normal distribution. The same thing happens with the distribution of the different, sums of squares for the chi-square. So we need a sufficiently large sample size, and we need sufficiently large expected values. The common rule of thumb is that you should expect 5 or more observations for each of the groups that you're looking at. If you can't expect 5 or more, then you should use a more exact test, like the binomial, or for the case of the independent multinomial, there's also a different test, the Fish's exact. Okay, you're also assuming independent observations, which should be sort of a given, simple random sampling. So there's no equivalent to a paired test. So with the t-tests, we had paired tests. With the ANOVAs, we had repeated measures. With the chi-square, we don't. When these are violated, we can use multinomial, binomial distributions, or other tests, and we're not going to